All right, hello everyone. Thank you organizers for putting on this very insightful and inspiring workshop. It's really a pleasure for you back at Rice. I got my PhD here almost 10 years ago, so it's really a pleasure to come back. So I'm going to tell you about this developing story about stacked TMD bilayers. Basically, there's something I wanted to say, but then more recent experiments, so I'm not sure I'll get through everything I want to talk about today. Let me just start by thanking people who did the work. This is really driven by Daniele Guerci and Valentin Kreppel, both postdocs at CCQ and the Flatiron Institute, and this is all really a collaboration with me with them. It's also really benefited from collaborations with Jed and Andy, and this is Andy's student, and I'm Chi. Okay. So, where I'm going to take us today. I'm going to give a basic introduction into moraine materials. We've already been discussing them, but I'd like to get maybe a very broad perspective on it, and then how to find new phenomena. And then I'll get into what we want to try to do to them, stacking or just stacking TMDs, but I'll review the twisting. And then we'll get into doping them and how this, I can't really see this pointer at all. Anyways, okay. So we are going to realize this heavy fermion emulator, and then if time permits, I will get to this solid state realization of a P-wave BCF-BC transition, which is searched for a very long time in cold atoms. And I think this is really going to be the best way to do it. There's actually now a lot of experimental proposals following our. Okay, so let's take a big picture perspective on how we got to this point in moraine materials. So it came with first is mechanical exfoliation, and then the realization that silicon dioxide was a very bad substrate to the trapping charge disorder. And then the most recent development is the Terran stack approach, which allowed accurate stacking and twisting of graphene layers. Like that. I don't know if there's another pointer somewhere. Anyways, nowadays, though, we have other materials. We have transition metal dichalcogenides. This will be the focus of today's talk. All of these are van der Waals bonded between these 2D sheets. We also have high temperature superconductors, visco. These are being twisted as well now. Though not twisted in the monolayer limit, they haven't realized the monolayer limit. So this, I think, in my perspective, this is just the beginning. If you actually look at how many materials can be exfoliated, there's over 1,000 potential 2D materials. So I really think that the sky is the limit, and it's really exciting to see what the field is going to go. Okay, so nowadays we have basically different ways to classify these problems. We have homobilayers, as if you stack and twist the same material, or you could just stack two different materials and the lattice mismatch could potentially be enough, or you could twist it. And these systems are realizing a lot of the conventional condensed matter physics that we are used to, and we're seeing this kind of amazing emerging phenomenon that we've been searching for in a controllable way, and now we see it all the time. For example, superconductivity, a lot of insulators, and orbital magnetism. But when we get to this multi-layer dimension of the problem, I think it really takes us beyond what we think of as Hubbard models and so on and so forth. Quasi-crystal and strong correlations are going to come and play a major role here, as we're already seeing from experiments. So that's a very interesting frontier where we're going to have to depart from what we're comfortable with writing down effective type binding models. Okay, so I'll put that as maybe some thoughts. So at the point when we started working on this problem, we were thinking, what other systems can we emulate? Sorry. And we started thinking about heavy fermions by doping these light insulating states that people have been tuning through. Okay, using electric fields, we'll talk about. And also iron nicotide is an interesting angle to think about as well. So what else can we find? So today, as I've told you, we're going to talk about heavy fermions, but we're also going to find that by just enlarging this model, taking into account the next nearest neighbor interaction, which is quite large in the material, we can find ways to realize this P-wave BC topological phase transition. Okay. So let's see if I get there, because I had a really nice talk by Tim Fall yesterday. I brought out this ferromagnetic state, and I wanted to see some about this. Okay. So to do this, though, to get to a heavy fermion-like thing, we want localized moments. Itinerary carriers. It's very natural to think about stacking two different materials. One that maybe is more correlated, and one's more weakly correlated would be the idea. Okay. Our building block are going to be TMDs, as Kim Fai said yesterday. These have been used to death now. So you can think of these as a 2D honeycomb lattice, even though the structure is slightly more complicated, and made with transition metals and alkalides. And you can really think of a TMD as something like graphene broken inversion due to the AB sublux that you're breaking, and a large isospheroid coupling. So if you do a K.P description, you're one of the values, you're going to see something like this with particular energy scales. And you can do some sort of expansion near one of these values, and you see these whole bands that are spin value locked. So each value is locked to a spin. This will be an important part of these materials. Okay, now let's start putting it together. So in the homo bilayer case, you can adjust it via twist, but for the hetero bilayers, you have this lattice offset or mismatch, which gives rise to a distinct Moiré pattern that has a cutoff that's multi-distinct. And so in the case of homo bilayers, you can tune this, but this one actually cuts off, okay? And you get basically different, by different stackings of these, you can have different ground states and different magnetic states as well. So choosing the stacking can vary the ground state in an interesting way because of the Isaacs framework. Okay, so this is a very nice review by Kim, Phi, and G, and it's basically describing distinctions between these TMDs and twisted bilayer graphene. For example, there's no special angle, there's a wide range of flat bands. You don't have long obstruction, the spin value locking makes things simpler, small interlayer tunneling, so on and so forth. So it's a very nice playground to think about Moiré materials. You're realizing the Hubbard models and so on and so forth. And this is really kind of motivated by Alan McDonald's work on this, where they basically pointed out these tunable Hubbard models. So the minimal model you can write down for the band structure kind of picture is you have basically the potential for the bottom layer acting on the top and the potential for the top layer acting on the bottom with some interlayer tunneling. Based on the fact that these are spin value locked, they ignore this interlayer tunneling to start, and you get this rather simplistic picture over here, which you can wanderize and build a Hubbard model, and you can see it's very tunable as you tune the Moiré scale. As a result, experiments have been done, and they're able to see tunable metal-insulated transitions in these TMDs. And so this is MOT2 stacked on WSC2, no twists, and this is by the WSC2. Okay. So from a theoretical perspective, very nice paper by Liang's group, where they basically worked out these kind of Moiré models that come out of this stacked system. So stacking MOT and WSC2 gives you a Moiré pattern of about 5 nanometers. This is just from the lattice mismatch, no twist. And so M is referring to the metal, X a calcinide, and so this is the kind of different stacking arrangements we can have. Okay. And as a result, you get tunable bands. Tunable via this displacement electric field, and as a result, you realize some effective model on the Moiré scale with the tunneling hopping between these sites and an interlayer tunneling, so interlayer tunneling, which is hopping between the red and the blue, and then tunneling between the same things. Okay. So if these experiments looking at these tunable bond insulators, and we come back to this, and so this is the function of these different kinds of top and bottom gate voltages that can be applied. And as you see here, this is a Mach insulating state, very large resistance, shown as color, and coming out of that as a function of the displacement field is this quantum Hall state. That was seen to be basically, having basically a quantized Hall effect, and they were able to construct a phase diagram shown here, which shows how this Mach insulator can go into a quantum Hall state all the way into a metal as a function of displacement field shown there. Okay, so here's our Mach insulating state. I want to know the dope away from this Mach insulating state by selectively gating one of the two layers. So what do I mean by this? So let's just think about this a little bit more. So I haven't done any gating. I completely filled my lower Hubbard band or MOT2 by 1 electron. My WSC2 is empty. Okay, so I can think of a lattice of local moments and no carriers. And now I'm going to lightly dope WSC2 because I can do this selectively in the experiment, and as a result, I'm going to fill this dilute band of carriers with electrons that are going to be hopping around that are going to be interacting with this Mach insulating state of local moments. And I'm going to try to convince you that this is going to realize a combo lattice. It's a particular way. Okay, so that's my motivation introduction. And I'll go on to realizing this heavy fermion emulator. Okay, so as I was saying, we can selectively gate these two. So we're going to keep MOT2 at filling of 1. And we're going to put electrons in the WSC2 layer. Okay, and the experiment Kim Phi was telling us about yesterday, they were able to see a nice T² and mass enhancement indicative of like a heavy fermion state. And as a function of magnetic field, they're able to tune out of the heavy fermion liquid state and see a jump in the carrier density by extracting it from the whole body. Okay, and so this jump of one whole formal array unit cell is very much like a large to small Fermi surface transition driven by magnetic field. So this is something we were really trying to describe in our theory. And so what we do is you write down this effective model on the Moray scale, so I'm skipping a lot of steps. So I'm going from this Moray scale to a Hamiltonian that lives on these Moray sites. Okay, I have this picture in mind. This term arises due to this Ising-Springer coupling, and it'll be different based on my stacking configuration. And I have interlayer tunneling, which I can treat conservatively. So both these scales, the interactions in these bands are actually comparable, and I'm going to drop the one in the W layer based on the size of the bandwidths, but this is going to come back to bite me, and we'll talk about this later. Okay? So just bear with me. So we're going to treat the W band as that looped as well, and so that's going to be a weaker effect as well. So it's reasonable to ignore it, but as I just said, it is going to have an effect in the very low doping style. Okay, let's come back to that. And under this limit, we can now apply a Schroeder-Wills transformation trying to map to the local moments on the MO sites. Okay, and so what you realize is this Kondo lattice model, Kondo Heisenberg Hamiltonian, where the dispersion is affected by this Ising-Springer coupling, and you get this spin valley locking of the two K and K prime of the Moray brilliance. Okay, and our electron density here X, and what's amazing about this problem is this is a Kondo problem tunable by density. So it's very different than what we're used to. Why does this happen? So this is actually how I got really interested in this problem. So basically, you have this Kondo coupling. It's a product of these two hybridization functions. And because of the structure of one side having to hybridize with a triangle, you get a P-wave hybridization when you expand this near K or K prime. And this nodal hybridization is pretty non-trivial. And if you actually average out your Kondo coupling over the Fermi surface, you'll see that it's tunable by density. So there's a Kondo coupling tunable by density due to this P-wave nodal nature of the hybridization. This is also going to give us topology, as I'll show you in a second. And just to give you some nitty-gritty, we use the basically Abercrombie fermions and sort of mean field decoupling. As it's rather standard. I'm just listing the equations here. Okay, so solving this problem, zero temperature, what we find is an anti-ferromagnetic state with a small Fermi surface with an ordinary wave vector of 2 pi over 3 and a large Fermi surface heavy Fermi liquid state. Okay. So this is obviously problematic based on Tin5's talk yesterday. He found this to be a ferromagnet. Let me come back to that. Okay. So anyways, if we now look at a cut through this phase diagram, with these mean field parameters, here's my magnetic state, here's my heavy field liquid state. This transition is first order within the mean field limit. It's a very interesting question to think about going beyond that, and if that remains first order, we can continue this. We also see this large effective enhanced mass as indicative of the heavy field liquid state. And so if I now describe this heavy field liquid state, this nodal hybridization is what I was trying to argue is what's interesting. And you can see that here, when you solve this low energy dispersion, what you find is a topological hybridization gap actually opens. So it's very much like a topological heavy fermion problem, actually, though it's not played the symmetry is not played by orbitals, it's played by what's coming out of the Moray problem. Okay, but it's not truly anything to be quantized because you actually have a band crossing the Fermi energy, so it's actually metallic, though you have these topological gaps opening. Okay, so you won't have any quantization, but you could have interesting edge nodes that would maybe not be protected, for example. Okay, and you see this mass generalization over the entire Fermi surface, and this anomalous Hall effect is due to this very curvature distribution I'm showing you on the very right. Okay, so just to summarize this state, you have the density tuned Kondo temperature, and so that effective mass is going to be directly tuned by your density, and this qualitatively agrees with the experiment, though our Kondo temperature is basically too small. The comment I will come to later. Okay, so if you now apply magnetic field, try to connect to the experimental observations, you can get out of the heavy field liquid state or this magnetically ordered state via inducing a ferromagnet, and actually, as soon as we turn on the magnetic field, this topological gap, this topological gap opens. It's 5 minutes till questions. Yeah. Okay. So anomalous Hall effect is induced at any finite magnetic field in either phase. Now, if I look at this heavy field liquid state, when I polarize the spins, I kill that state, and I have this jump that they saw in the experiment. So this captured that jump in Hall density quite nicely. Okay. But as we saw yesterday, the talk by Kim Fine showed that this is not an antiferromagnet with 2π/3 order. It's a ferromagnet that's insulated. It's not at all what our theory is. So, but this came out after the paper, so it's okay. You know, let's spend our time. So what's going on? What did we miss? And so Daniela and I were really talking quite a bit, and he realized that these correlations in the W band that we think are really key. And so if we actually go back and do perturbation theory in the interlayer tunneling, but keeping the interaction within the tungsten, sorry, the W band, what you'll find is you can derive basically a single impurity model perturbatively now in these interactions. We can't do this properly, but what you'll find is at the impurity model level, that P-wave interaction that we had giving us the condo effect actually is competing with other channels. Okay, so this interaction in the band gives me other condo effect channels, and these can actually win if you do the renormalization group calculation, which we've done for the single impurity problem. At low density, we find that these moments are free. Okay, that's the first statement. So the moments are free. So now I have free moments. I have this interacting W band that's spin value locked. That Hubbard interaction is going to basically want to put all the electrons into one of the values. So it's going to value polarize, which gives me a ferromagnet. Okay, that ferromagnet breaks time reversal symmetry. The strong disorder with doping gives me a unitary class problem in 2D. I Anderson polarized. Okay, so I explain the ferromagnet observation from Tim Phi actually quite nicely, and this is work in progress. So please don't write it up before we can. Okay, and some other thoughts before I'm maybe I'll just stop before you put this part. Let's see, basically, there's arguments that this heavy Philip state might be disorder dominated. And actually, I think this is why our TK is so small, is because if you actually look at disorder carefully, it actually enhances the condo temperature. It doesn't suppress it like was being argued in this PRD. So if you actually incorporate disorder in the interfacial coupling, you actually find an enhanced condo effect, not a suppression. Okay, so this is some thoughts. And the last thing is the nature of the transition beyond mean field. Is a very nice paper by Chinel's group that just appeared, where they did a different slave article description than we did, and that's a pretty nice paper to take a look at. It provides more of a global perspective on this problem. But based on Kim Phi's recent paper, maybe we need to think about incorporating disorder and interaction within the W band into such a description as well. Okay, so what happens about the next nearest neighbor interaction? We haven't talked about it all. It's also sizable. So I'm going to try to do this in a lightning fast way. So basically, okay, so now I'm coming to this is the last part of the talk. Okay, and basically, if you actually take these Y functions in the upper and bottom down, sorry, top and bottom layers, you'll see that they have a significant overlap with next nearest neighbors. So if you compute this matrix element, it's actually about half of the interaction scale. It's not small. So let's put it in. Okay. And so if you put it in, and you now, there's several different stackings you can take. And we're going to take a particular stacking that we know to be interesting because we've done the calculations. We want to take a stacking that's an AA stacking, and that's going to come and gives you a ferromagnet in the strong coupled layer. Okay, and you can expand at the bottom of the band in the weakly coupled layer. Here's my Morey brilliant zones from the last mismatch, and what you find is basically this is your dilute band, and this is the interaction. You have the singlet and triplet channels, a lot of channels. But when you decompose it, you can see rather nicely that these scales all become negative, and this one is our dominant scale that wins, and it becomes negative even though all the interactions are repulsive. Okay. And in this triplet channel, you can now have pairing, and this is our dominant pairing channel. If you now look at that superconducting state, what you see is there's a gap in the BDG spectrum. It has a non-trivial spin texture. And if you do the Landau theory on this, it locks these two phi plus phi minus together. And as a result, what you find is that this is a topological superconducting state with a Z2 index. There's a quantized spin Chern number and thermal Majorana edge modes in this ground state. Okay. Now we take another limit and to give you a different perspective on how you get this attractive interaction, but then make it a bit more intuitive. So let's take a local picture and try to form a local pair and think about the dilute. So that was my the opposite limit that I just talked about is the BCS limits. Let's think about the BC limit of these pairs. And so basically we're doing the same stacking, and now we're going to do that Schrieffer-Wolff transformation I had before, keeping all these details. and you find this kind of a mess of an equation, which is not very illuminating whatsoever, but let me give you some insight. So here's my configuration consisting of, let's say, one electron. I can now add one electron, so I have a 2e electron. It's going to cost energy, but it turns out due to these virtual processes, you can form a bound state that lowers the energy. Okay. Similarly, this process is basically another excitonic process that's going to also be renormalized, but not as low in energy. So you can actually form a 2e exciton that has the lowest energy, and that interaction becomes negative after some critical value. So you can solve for these bound states. You can find where I have a binding energy of these bound states, and in this region where I have these bound states, which is the limit of the superconductor, everything's topologically trivial. So now I can put these two limits together. Okay, so I have here's my from weak to strong coupling, basically from my BCS to BEC limits. And so in my BEC limit of these basically local pairs, I have a gap with no spin short number. That gap closes and opens, and I get a finite spin short number that's precisely the BEC to BCS transition that realized in a solid state context. So if I had zero temperature, this is a true topological phase transition. Okay, I'll just watch my conclusions, and thank you for your attention.
Thank you very much.
Nice talk, Jed. So let's pick your brain a little bit. Why do you need to work so hard for the ferromagnetism in the sense that the root barrier limit, you have lots of heavy terminals that actually are ferromagnetic water?
So this is okay, yeah, that's a good question. All these let me just go back to my Heisenberg. A good question. So there's no RTKY. So this Heisenberg coupling is coming from the Hubbard model. So I think it's a little different.
I understand that, but the RTKY doesn't exist.
It does, and I think so. We have to add it to this, and then yeah, it's a great question. We have it covered.
Thank you.
Yeah. It'd be a ferromagnetic RTKY, but Daniele's been arguing it's subleading too, but we haven't done the calculations. So.
Thanks for what justifies using every constant terminals over other like splitting?
Oh yeah, no, I'm not getting into that. I mean, this is step zero. You do what you know will describe the heavy forming liquid. That's what we're kind of after. But if you want to describe things beyond that, you have to work harder. So I mean, we just kind of use the conventional vanilla description of the heavy forming liquid at the mean field level.
Okay.
Yeah. But I welcome you to do beyond that. Okay.
Very nice talk. So I want to know if you think as a very dilute conducting electron limit, will the higher Moore bands coming from the MOT2 layer based on important volumes of modular phenomenon? If we are only doing this two band.
I think that the other band is pretty far away with my cartoon. I mean, I think that this one you're talking about?
No, I'm saying the higher Moore bands.
Oh, the higher Moore. You mean just from the downhole?
Yeah.
And the TMDs are pretty well isolated. I don't have too much intuition beyond like screening effects of the interactions or changing the numbers, but yeah, it's a good question. I'm not sure. Not trivial question to answer properly. But yeah, I'm just saying that the isolating gaps in TMDs are not as sensitive to relaxation and everything like graphing. These are pretty well isolated.
Let me ask something. You mentioned that there are already experimentalists interested in this delay.
Yeah. So about Blue, I should have had some citations on there. Basically, we had so we had one particular sequence of excitons. This may not be the best one. And it doesn't really matter which set of excitons you choose. You just need to realize basically this bound state. And you also, and the other thing is that I didn't mention this at all, this is actually, there's a tuning here where you can tune the scattering length via Feshbach resonance of the excitons. So it's very much like the pulmonary setting. So you can go from the VCS to VC side by changing the sign of the scattering length in the P wave channel, all optically addressing the static TMDs.
Okay, thank you.